let me share another screen. So we will move on with our chapter 7 today. Okay, so hopefully you all see this new shared screen now. Okay, hexadecimal addition. We learned how to convert hexadecimal to binary and vice versa. So we need both direction in doing the hexadecimal addition. So for the hexadecimal, we know F is 15 in decimal. So F plus 1, F is the biggest value that we can represent with one single hexadecimal digit. So F plus 1 we have that will generate a carry over to the next bit. So it becomes 1 0. This is not 10 in decimal. 1 0 in hexadecimal is 16. 1 1 0. So 2-bit hexadecimal values. F plus F. So you convert F into decimal is 15. So 15 plus 15 is 30. So we have 1E. So 1 here, this bit is 16. E is 14 in hexadecimal. So 16 plus 14 is 30 in decimal. So I know you have to do this forward conversion. So convert hexadecimal value into decimal value and then add them together, then convert this decimal addition back to hexadecimal. That is the step we are going to take. But if you are really good at it, you probably will be able to calculate this in hexadecimal. Let's have a look at this example. So we have 4-bit hexadecimal values. 2 of them add together. So this H here indicate it's a hexadecimal value. So we have 4 hexadecimal bit for the 2 values that we want to add together. So first step is to convert every bit into its corresponding binary, into its corresponding decimal value. Okay, 2 and 6, we don't need to convert, we just move them here. 3 is also just move over. And this B is decimal 11. So write them down in bracket. So this is very clear. So for the second number, 1A9C. So you write 1 and 9 down here without any change. For A is decimal 10. C is decimal 12. So you write them down in this manner. The next thing is to do the addition. So 3 add 12 is going to be 15. Again, we write it down in a bracket to indicate this is the decimal value, and then we will convert them all together. So 11 plus 9, that gives us 20. 6 plus 10, that gives us 16. 2 plus 1, that's 3. So we can have a quick look because there are 2 values here, 20 and 16. They're both greater than 15. So that will tell us there will be a carry value, carry bit. So how do we do that? So this 20, it will generate a carry bit. So when we have a carry bit, so that means it exceeds 15. So the carry bit indicate is 16. So 20 minus 16. Yeah. Okay. So that should be corresponding to these rows. 20 minus 16 is 4. So this 4 will be generated. So, and when we have 4 added here, we have another bit that will be carried over. So this this carry bit is actually generated by this 20 here. So 20 minus 16, that is going to give us 1 carry bit. Then we have a 4 left on this digit. So this carry bit need to be added to the next sum. So that's the next bit, 6 and 10 add together is 16. 16 is going to generate another carry for us, carry bit for us. So that is going to be this carry bit. So we have another carry in from the previous bit. So that one will be will be written down here in this bracket. So the next carry bit will be added to this 2 plus 1. So in total, we have 4 here. So let's have a look at here. So 4, 1, 4, 15. We need to convert this 15 into F. That's a hexadecimal. So we end up with 414FH hexadecimal. So this is how we do hexadecimal addition manually. Although you can just run this a lot quicker with your calculator. So, but you should know the step-by-step process for doing it. Hexadecimal subtraction is similar. So we have, instead of carry bit, we have borrow bit. So let's have a look at this example. I won't go through this conversion for digit to digit conversion. So we just take it from this converted value, and then we put it in this subtraction. So when we need to carry 1 bit, remember that when we need to borrow 1 bit, remember we need to subtract that borrow bit from the higher digit, and then add 16 to the lower digit that borrows this bit. For example, this last bit here, we have 3 minus 12. So it's not enough. We need to borrow 1 bit from the next bit, from the next higher bit. So this is the 11. 1 bit get borrowed, so it has only 10 left. So this is how we get 10 here. Okay, so this 3, it borrows 1 bit from the next bit. So it will have another 16 added here. So in total, we have 16 plus 3, that's 19. So 19 is enough for us to subtract this 12. So 19 subtracts 12 gives us 7. So this is how we get it here. For the next bit, 9. So 10 minus 9, that gives us 1. So that's straightforward. And the next one is actually, this is the previous 6. 6 minus 10 is not enough. So we have to borrow 1 bit from here. So this 2 becomes 1. So that is this one here. So 6 borrowed 1. So that 1 bit in the higher bit is going to be 16 here. So that's how we get 16 plus 6. That's actually 22. 22 subtracts 10 gives us 12. So the last step is to convert this value into hexadecimal. So we only need to convert this 12 here. So 12 is actually C in hexadecimal. So we have C17H. So that's the subtraction result. Okay, so okay, so Ria, since we are on this page, can you let me know where for the addition? Okay.
On slide 25, should it be like if we had 16, would it be 0 carry 1?
Okay, so oh yeah, oh no, actually, so what happens is that you're right. So this is 16, this is 10, but remember that this is the 1 carry bit from this bit. So we have 11 plus 9, that's 20. 20, we have 4 and then 1 carry. So this carry bit is moved from this bit to the next. So we carry this bit here, this carry bit. So this is the carry in bit we learned. So carry in bit need to be added with these two numbers. So in total here, we actually have 21. So 21. So this one falls down and we have another 16 carried to the next bit. Does that, is that clearer? So does that make sense here?
Yes, thank you. Yeah, I forgot that we were carrying 1, so we had to have 17 then. So it'd be 17, 1 carry 1.
Yes, so this carry bit is from this bit. So it needs another arrow to be, yes, that's right. So 6 plus 10 plus 1 is 17. So 17 is 1 and another carry here. Okay, so so in this the first group, it doesn't have the carry bit. So here we have carry bit written down here. So that's the addition. Okay, yeah. 1 1 H equals 17. That's right. That's right. The 17 hexadecimal. That's correct. Okay, so BCD code. You are all familiar with this BCD code now because we learned this in a 7-segment display. So BCD is a binary coded decimal. It's a code used to represent each decimal digit of a number by a 4-bit binary value. So that means we only use 0000 to 1001. So this is 0 and 1001 is 9. So we only use these 10 combinations. For the other binary codes, 1010 to 1111, they are invalid. So what do we do with invalid? In key map, we use don't care to represent this invalid value. So it's also called 8421 code. So 8421 is actually the decimal weight of each bit. So it's another name for this BCD code. So we have these 2 examples. We are familiar with how to convert it. So just to use 4-bit binary to represent each decimal code here. Okay, so access3 code. So it's a BCD code formed by adding 3 to its true 4-bit binary. So add 3, that's add 0011. So that's access3 code. So it's a self-complementing code. A negative code equivalent can be found by inverting the binary bit of the positive code. Okay, so inverting the bit of this excess 3-digit yields nice complement to the decimal equivalent. What does that mean? So let's have a look at this, the meaning of this. So we have 3. If we write it down in binary or BCD code, binary coded decimal code is 0011. And if we want to generate the access3 example for this, we need to add this value with 0011. That gives us 0110. So this is 6 in E3, that's access3, 6 in access3. So if it's value 1, the BCD code is 0001 plus 0011 to generate this E3, we have 0100, so 4 in E3. So the 4, this value is E3 form to represent the BCD code of 1. So we have to be clear here with all these definition. So if we complement 1, so complement 1 means flip every bit. So this is 1 in E3. So how to represent decimal value 1 in excess 3 coding? So that is 0, 1, 0, 0. To complement that means flip every binary bit. So we get 1, 0, 1, 1 in E3. So this is the code for 8. This is the code for 8. Why? Because so the 8 value in E3 is so 1, 0, 1, 1. I want to do the conversion. So 9's complement means 1 equals 9 minus 1 equals 8. So that's self complement here. So let's just take it that way. So when we learn 1's complement, it means every bit need to be flipped, and every bit need to be flipped, right? When we learned 2's complement, that means we need to flip every bit plus 1. So this excess 3 example, so excess 3 coding manner actually gives us nice complement. So this is just to take it by definition, I would say, just to take it by that definition. Greek code is, I would say, is more useful or more common than the previous excess 3 code. So so based on the application-wise, Greek code is very useful, and you already know what it is from our key map. So if you remember when we write it down, the combination for the key map for the rows and columns, we have to make sure that every row has only 1 bit changed. So that's why we can't just write down 0, 0, 0, 1, 1, 0, 1, 1. We have to swap the fourth and third rows. So that is 0, 0, 0, 1, 1, 1, 1, 0. So I have repeatedly mentioned this many times. So for Greek, that is actually the Greek code definition. So a binary code that progresses so that only 1 bit changes between 2 successive codes. And I can tell you why this is important. So if you build a counter, you count the value up. If we are counting in general way, so from 0, 0, 0, 0, for example, 4 bit up to 1, 1, 1, 1. So when the counter reaches 1, 1, 1, 1, every bit will flip back to 0, 0, 0, 0. So that is for a general counter. So many other cases, you will have more than 1 bit flips at a given clock rate. So let's assume that the counter will count up at every clock rising edge. For Greek code, this is very different. So every count, you will only change 1 bit's value. It is very important because in hardware, if you only have 1 bit flipped, it's very less likely for you to get crosstalk noise. So if you have many bits, they are all flipping at the same time, you get the crosstalk noise. And when this noise gets bigger, it will create bigger noise to cause other stable bit to change value. So that is the error. So error can be generated by this parallel bits flipping together, so toggling together. So if we have a Greek code counter, that means we have reduced the risk of getting error from crosstalk, getting error from this continuously toggling bits. Another reason that is important, because if you have one bit that's changing changing from 0 to 1 or 1 to 0, that means you are consuming less power. So only one bit is toggling. But if the system if the hardware has many bits toggling at the same time, then that means it's consuming more power. So these are the reasons for gray code being so popular, implemented as a counter. Okay, so the equation for gray code. So how to generate the output to make sure that every time only one bit changes, we use XOR. We use XOR. So G3 is the most significant bit, equals B3. So that's the binary code output. So G3 is a gray code output, bit 3. So how do we generate these different bits from binary bits? So G2 equals B3 XOR B2, and then G1 equals B2 XOR B1, G0 equals B1 XOR B0. So you can probably see the pattern here. So for ASCII code, this is not a new concept. So ASCII is short for American Standard Code for Information Interchange. We know it's 8-bit, so in total we have 256 different combinations, and it's used to represent. So that's the extended. This is the expanded, widespread expanded ASCII code. So previously we only have 7-bit, so that's 128 different combination, and we use it to represent letter, numbers, and special symbols. So now it's get extended to 8-bit, so we can represent more special symbols or characters. So that's the ASCII code. Binary adders, I already talked about it, the half adder. So that's at the start of the chapter, we learned the half adder. So it is circuit that will add 2 bits, 2 single bits together to produce a sum bit and a carry bit. For a full adder, we have another additional input that is carry in. So we can generate a full adder using 2 half adders. So this is what we have seen before. So 2-bit addition, it will generate 2 output bits with one sum bit and then 1 carry bit. So that's the half adder. So we have this truth table for the sum bit and then carry out bit. The equation is the sum bit equals A XOR B, and the carry bit equals A and B. So this is the truth table Boolean expression. And the hardware circuit symbol for half adder, we can see we have 2-bit in and then 2-bit out. That's for the half adder. For a full adder, the additional bit here is the carry in bit. So we still have carry out, we still have A and B, we still have the sum, and we have an additional carry in, C in. So this equation here is going to be the carry out bit equals A XOR B and C in, the carry in bit, or A and B. So for sum bit is A XOR C in. So that's the output sum bit. For the symbols, similar to the half adder, but with the additional carry in bit here. So this is the detailed circuit for full adder. So the gray area, green area is a sum. It should be a symbol for half adder. So we see we have two half adders. So within this green area is a XOR gate and an AND gate. So this is a half adder. This is another half adder. Together we have a full adder. We have to add another XOR gate to generate the carry out bit for the full adder. So this is just simply reduce those detailed green area into the half adder symbol. And we have the parallel adders, which is to use multiple full adders for individual bits, and then repeat that to make them work in parallel, connect them in parallel. So we have a multiple bits added together. So instead of one single bit, we can have a 32-bit value plus a 32-bit value. So that means we have to have a 32-bit 32 parallel full adders, and then chain the carry out bit together to create a ripple carry out bit. So what do I mean by that? Because with a multiple bit, we still, although I said 32-bit, that is the data value. For carry in bit and carry out bit, they are always going to be only one bit. It doesn't mean that we have a 32-bit data value plus another 32-bit data value, then we will have a 32-bit carry in and a 32-bit carry out. That's not the case. For the carry in and carry out bit, it's only going to be one bit long. Let's have a look at the parallel adder, the symbols. For this example, we only have 4. So 4-bit addition, 4-bit adder. And here we have the most significant bit. So the carry out bit for this 4 parallel adder, it will be the output of the carry out of the most significant bit is going to be the total carry out. For the carry in, it's going to be the carry in from the least significant bit. Okay, so we have 1 in and 1 out for the carry bit. And for the data, we will have 4-bit data in for each binary number. So A4, A3, A2, A1. So that's a 4-bit in, and B4, B3, B2, B1. That's another the value B. So we have another 4-bit. Also, sum. The output for the sum, they are also 4-bit. So if it's a 32-bit value plus 32-bit value, we also have a 32-bit output. So that is the sum output. Ripple carry is how do we work out the internal carry in, carry out. So if it's an n-bit parallel adder, the carry out is the is generated by the last stage. The ripple adder is called because the final carry out is based on the ripple through of the carry in from the least significant bit. So that is when we have a look at so this is the circuit. When we have a look at this one, so what we have here is when we have this carry in bit from the least significant bit, this carry out bit, where does it go? So this carry out bit needs to be connected to the carrying bit of the next bit. So that's what we mean by ripple carry. So this slide doesn't show the connected circuit, but we should know that the carry out bit from the bit 1 need to be connected to carry in of the bit 2. oh, hang on. So hang on. Yes, so that's right. So that is that is the report through this total n-bit parallel adders. So that is what we call a report carry adder. So let's just quickly talk about this propagation delay concept. It's important in that when we talk about hardware, so when you do the programming in C, you probably never considered the propagation delay, how long it's going to take the hardware to do the calculation. But when we implement this in VHDL, we do need to consider what is going to be the propagation delay. First of all, what is the propagation delay? Propagation delay is the delay that we get for a logic gate to give out the stable output. So what do we have inside the logic gate is based on MOSFET technology. So what is a MOSFET technology? It's a MOSFET. So when MOSFET does switch from 0 and 1, it takes it takes a tiny delta t. So delta t is a very small time. So that is the time it takes for us to see the reliable output. For example, you have an AND gate. You have two input, A and B. A and B, the output is Y. So when we change the input value, the output doesn't change immediately. There will be a very small time delay. That is a propagation delay of that gate. Although we can, most of the time, you can ignore that because it's a very small delay. But if you have a very long circuit, so very long propagation delay, that means if we have this ripple carry, that is going to be 8 gate here, AND gate and OR gate. So all this propagation delay of the chained together gate will be added together. So the delay itself, the total propagation delay becomes significant. So we can't ignore it after chaining so many different gates together. So at this time, we have to consider to use other design technique to make sure that we don't run into a too long propagation delay. That will affect the output of our digital circuit. So in this case, we have 4-bit ripple carry adder, so chained together adder. So carry in from the previous bit will be carry out of the previous bit will be connected to the carry in of the next bit. So each adder give us 2 delay because let's have a look at these here. So for each adder, the input goes in to need to be the input will pass the XOR gate, and there will be also another AND gate. So the full adder for the delay for 1 bit, a full adder, it will pass how many gates? When we talk about the propagation delay, we normally go check the longest propagation delay path. So you can't go use the smallest delay. We have to go check the longest propagation delay path. So for this full adder, it will give us 3. Add this one, it will give us actually 3 propagation delay, but actually here is A XOR B to generate the sum. For the sum bit, it will only have 2 gate logic delay, 2 gate logic delay. For the carry bit here, it will have also 2, so it will have 2 delay. from the carry in bit to the carry out bit, it will have 2 delay. So because we here we get carry in here and then pass this AND gate and then pass this OR gate, this carry out bit here will have 2 gate delay. So we have to separate the input and output. So for it gets complicated very soon, very quickly. It's just a very simple example for this full adder to give you the idea how to work out the simple propagation delay. In real life, you never need to do that, because in your VHDL design, what happens is the Xilinx tool, the nice Xilinx tool will go through all your design and work out the propagation delay for you. And when you read the report, it will tell you what is the maximum delay and what that is. Normally, it will be in nanosecond. So, so when you define your circuit, you will say, I want my propagation delay to be maxed at this value. Let's say I want my biggest maximum propagation delay to be 100 nanoseconds. So if we call that constraint. If you say, I want this design, then the software tool will take your command and try to route your design to make sure that the propagation delay don't exceed that maximum value. However, if your VHDL code is not very good, then the design tool will not be able to accomplish the mission impossible. So you have to balance these 2 techniques. First of all, you have to make sure that you write the efficient VHDL code. If you can't meet the timing requirement, if your propagation delay is too big, you can quickly try to set the constraint in the software to let the Xilinx tool to help you to do that. If the Xilinx tool can't help you with it, if it failed, then you know that you can't go through this quick fix. You will have to go back to your VHDL code to rewrite a more efficient code to meet the timing requirement. Okay, so that's the additional information there for related to the future design. Back to our report carry. We know that the 32-bit adder will, like the one that we use in our general PC, it will incur 64 gates propagation delay. So that's pretty long, right? That's a pretty long propagation delay. So that looks like this. So we have carry. So this intermediate carry out bit. Actually, they are invisible. We don't use them anyway. So they are used by connect the carry out bit from the previous bit to the carry in bit of the next bit. The only one the only carry in bit is the first carry in. The only carry out bit is the last carry out bit. So this is the circuit, but we can see that the propagation delay is very long. So there is a technique to optimize this, which is this look ahead carry. We call it a fast carry bit, fast carry. So that is going to use a combinational network generally to create this fast carry out bit. So this is the additional logic that is used to generate a faster output. Balance between a trade-off, we will say, between the FPG resource and the speed. So this is what you always need to look out for. So whether you want the speed, that means less propagation delay. So the smaller the propagation, the faster the circuit. Or you can use more logic to work out the output. That means you will need more FPGA resource, logic gate, work out the output. So that means you have a faster speed, but you are using more FPGA hardware resource. So always balance these two. You always have an option. So that's the beauty of design. So you always can design your circuit based on your requirement, whether you want to circuit to run faster, or whether you want to use a less FPGA resource. Okay, so again, the carry look ahead carry. So we have already mentioned that. So parallel adder with component. So when we talk about parallel adder, we know that if we use the 4-bit parallel adder, that's 4 full adder components. So in VHDL, we can use the component, which is actually another VHDL file. And at the top level VHDL file, we can call this component. We can call these components that we defined previously in the component VHDL file. So we call this hierarchical design. Hierarchical design. It will make the design very clear, and it will make the very complex design. It will simplify the complex design. So let's say if you have a 32-bit adder, you want a parallel adder, you can define this one full adder and just to use this full adder component 32 times. Let's have a look at the connection of the parallel adder. So this is the full adder. This is the look of this is what Xilinx will generate for you automatically. So previously we saw this unconnected 4-bit full adder. So for this one, we say we talk about the carry in bit is connected to the carry out bit of this lower bit is connected to the carry in bit of the next bit. So in this example, the top one is a LSB or MSB. I'm going to ask you to tell me. So this A1 is a LSB or MSB. Think about it. So I can tell you, you need to, yes. So I have quickly good answer. So you have to see how it's connected, because I can draw the thing. Okay, so pay attention. I can draw the same schematics, and then I can erase all the connection. I will ask you to connect this full adder, and you can actually connect it the other way. I can tell you now I want A1 to be used as the most significant bit. So you have to wire it all different. But the in and out, they are going to be the same. So you have to, the thing that you need to wire carefully is carry in and carry out bit. So we can see the C0 is get connected to carry in. So you know this bit is going to be the LSB. So for the last bit here, we can't see it. So the carry out bit of the last bit is the total carry out bit. So this first bit here, the carry out is going to connect it to the next carry in is here. Okay, so this is how we connected internally, how we connect the parallel adders. So so this is if I ask you to connect it the other way around, you have to you can't see this. So for example, this one, the carry out bit will be connected to the carry in bit here, and then this carry out bit will be the final carry out bit. So think about how you need to connect these carry in, carry out. If I say, if I put the most significant bit, so on the top. So that's a quick modification for you to think about for connecting the schematic. Okay, VHDL full adder in so in the parallel adder mode. So entity definition, I won't go through this. So we basically have input output port. They are all defined in standard logic. So the architecture. So for this one, is only a single bit. So it's very straightforward. You just write down the Boolean expression here in VHDL. So pretty simple here. And if we want to use the parallel adder, we will need a separate component. What is separate component? Is this file we just saw? This is a VHDL code, standalone VHDL code for 1-bit full adder. And we are going to use it as a component in our top level VHDL. So this top level VHDL will include this component and then use it for 4 times for the 4-bit. So in addition to this VHDL code, in the top level, we have to include the component declaration. And where do we declare that? It is within the architecture, And we have to do the component instantiation statement. And where is the instantiation statement? Is within the architecture main body. Let's have a look at the example. Entity is going to be similar. Apart from the A, B, and sum, we extend it to 4-bit, 4 down to 1. 4 down to 1 is defined in such a way. So you may notice every bit now is everything now is defined as 4 down to 1 or 3 down to 1. So this is a 4-bit. 4 down to 1 is actually 5-bit. Think about it. We need 4-bit adder. Why do we need a 5-bit? That's because we have a carry out bit to take care of it. Okay, so that's why we have the 5-bit defined here. Let's have a look at the internal code. So internally, the architecture, start architecture, because within architecture we have a begin and end. So after the architecture, before the begin of the main architecture body, we have the component declaration. So the declaration means we have the component defined in another VHDL file for the full adder already, for 1-bit full adder. So the components simply declare that now we are using this VHDL file from this full adder defined in another VHDL file in this top VHDL file. So we are making a declaration here. So we are not redefining this full adder. So what the code is going to do is basically like in C code, you are calling a function because before you call this function, you have to include a library, or you have to define the function you want to use somewhere. So in your own C code or library code, this is the same. So we have this component. The component declaration, you need to add the part. So basically, the component looks like the entity defined in the components VHDL file. So in the VHDL file for the components, we have the entity at the top. So when you write your VHDL code, you copy that part in this component and name it as a component instead of entity. Now you have the component defined in this top level VHDL file. Okay, so and also we have to declare a signal, an internal signal called C. That's a standard logic vector C, 3 down to 1, so 3-bit. Okay, let's have a look at the main body. So begin. This is how we instantiate the component. So this dash is a common. Common doesn't compile. It's just for us to read what this code means. So we have adder one. So this name you can change. You can change the name because this adder one indicate this is adder one in your top level VHDL file. And the full underscore add here is something that you're going to always keep the same for 4 different adder, and this is a component name. Where did we see it? We saw it here. This full underscore add. So this is the full adder component name. And when we instantiate this component, you keep this the same because we need to do this for 4 different adder, 4-bit. So this name remains the same. Don't change that name. Otherwise, your top level VHDL code wouldn't know what you refer to. So this name indicates that you are referring this component is going to be the same structure as the declared component. For this name, you have to give it different name. So adder 1, adder 2, adder 3, adder 4. So this name, you have to change it accordingly, depends on how many adders that you're using. So basically, you're using one circuit, multiple times. So this one circuit is the same component, but you're actually taking these components and instantiate it many times. So within this instantiation, you have A, and is this symbol with A1. So what does that mean? So this first A is a part name of the components. It has to be the same as the one you defined in the components. So the first A before the assignment symbol. And the second A is completely different. It's completely different. So it has nothing to do with this part name A. Okay, you might get confused a little bit, but you will get used to it because they are not. So name-wise, they are not related. It just happens these two, they are both named as A, but they are not related. So what is this second A? This second A is a part we defined here. So this is the entity part. Different entity part name is A. So this A1 means the bit 1 of this A, this part name A of this entity. And this other A, this A is the part name of that component. They are not related, but you make them related here by connecting them together. What do I mean by that? You're connecting them together by assigning this A1, A bit 1 to this A part of the component. So this is like when you draw a schematic, you are connecting these 2 parts via a wire or a line. So this is what you do by assigning this bit here. So that is just 1 bit. This dot means we have another 3-bit components to instantiate here. I will show you the more complete VHDL code in a minute. So this is the entity generation. So this is the architecture component declaration. And here we have the for I 1 to 4 generate. So for this generate statement, as I said before, it is not a for loop. It's not a sequential loop. It is actually it's just a simple way of writing VHDL code. So VHDL will interpret this as you want it to copy this 4 times and then make 4 copies of this code. So basically these are parallel code, and 4 parallel components. Okay, so I will ask you to think about this one and write down the equivalent code without using for loop to generate. Just write down the simple VHDL code for this without this for generate statement. And then you will have to figure out the number here for I from 1 to 4. And by doing that, you will know exactly how to connect the input port signal to the output port for the entity. Subtractor, we finally moved on to this two's complement. So I mentioned that two's complement is extremely useful in doing subtraction in hardware, because we don't have subtractor. We have the hardware components we have is the adder. So how can we use adder for subtraction? We can use two's complement, because if we convert a negative value into two's complement, we can just simply add that value. So that is equivalent to doing a subtraction. So this can be implemented by implementing into the MPU, the microcontroller unit, microprocessor unit, very easily. So how to implement, how to do the two's complement in hardware, that is actually simple. So we this is a subtraction. So A minus B equals A plus B's inverter plus 1. So what does this mean? So as I said, negative B. So B, if B is, let's assume B is a positive value, minus B is going to be, let's say if we want to convert that in its two's complement, we have to flip every bit of B, that is B over bar. We flip every bit, that's one's complement. And then we add another one. Then what do we get? We get two's complement. So this part here is we are trying to convert the positive value B into its two's complement, which means is minus B is minus B. So this subtraction becomes addition. So we can implement this this right side of the equal sign using adder. Okay, so let's have a look at the circuit. So this is our simple adder. So this is our 4-bit A and 4-bit B. So for 4-bit B, we want to do the subtractor. We have to invert every bit. And this carry in bit C0 is connected to VCC. That means it's a 1. So what we have here, this subtractor implemented by an adder is actually what we have seen already here. So it's A plus B inverted B. So that is B with all this inverter here. So flip every bit plus this additional carry in bit, which is 1. So this is this is how we use an adder to implement a subtractor. So this is very clever, right? So, and it's very convenient because we don't need a subtractor, unique subtractor in the hardware. And what is more interesting is coming up. So we can use this one single adder to implement both adder and subtractor. So by using an XOR gate, because XOR gate can be programmed to be either is original form or is inverted format or is a complemented format. So that is when this one signal ADD over bar / SUB. So this signal is this is a name that we give to this signal. So this, if you read a circuit like this, you know when the signal is low, the signal is ADD because ADD over bar. So when the signal is high, the signal means SUB. So SUB is the active mode. So when this signal equals 1, B is complemented. When this signal is 0, B is true form. Let's have a look at the connection. So this previously we have XOR gate. Now previously we have inverter. So now we have XOR gate. So how does this XOR gate work? So when the XOR gate, actually the one input is this carry in bit. So is this ADD / SUB. So when, let's have a look at this. Let's have a look at when is 0 first. Okay, when is 0? So when is 0? B is its true form. Okay, so when is 0? So that means ADD over bar. So it is 0. That means it's an adder. It's an adder. So this 0 means 0 get carries in, and then we are adding B's true form to A. So it's very simple, straightforward. It's an adder. But when it is 1, that means B gets complemented. So B is inverted. Because it's 1, so we get 1 added to the carry in. That is the form we got previously here. So this is A plus B's complement plus 1 form. So that is when this ADD over bar / sub equals 1. So for this circuit, when this signal is 0, it functions as an adder. When this signal is 1, then it functions as a subtractor. So this is the cleverness of this circuit. So that's simply gives us the indications how to use the XOR gate to replace the previous NOT gate. So for the VHDL code, yes, I know. I'm a little bit over time here, 1 minute over time. So what we will do is I will let you have a quick look at the VHDL code now. And we don't have much left for this chapter, and we will complete this at the beginning of the next lecture. Okay, so I will wrap it up today, and I will check all the questions if you have any. Otherwise, I will see you next Tuesday.